Let me click on record there. Good. Okay, we're good. All right. So anyway, let's start with homework number 9 or quiz number 9. Okay, and this one we have a study that involved looking for an association between being a parent and suffering from anxiety. I guess some of you may have some experience with that. And so we'll take a look at this. Okay, so what do we have here? We have a contingency table where we have people that have children, people who do not have children, and how many other people in those groups, within those groups, had reported having anxiety or not having anxiety. Okay, pretty simple chart, right? But the question is, identify the two samples and determine whether they're dependent or independent. Okay, so what are we examining here? What we're examining here is an exposure. So our samples are going to be, if it's a controlled study or something like that, we would have an exposure and we would be looking for an outcome. So in this case, the exposure is whether or not a person has children or doesn't have children. So that would be the two groups that we're comparing the association for, the association with anxiety for. Okay, so have children, do not have children. So the two samples are the 832 women and children, 500 with children, 518 without children. Now, are they independent? Okay, so we've broken them down into they have children and don't have children, and we randomly sampled. I guess they must have said here they randomly sampled 832 women with children, without children. So there's no reason to believe that there would be that they would not be an independent sample. Okay, so there's an independent sample, or it has to be an independent sample if we want to analyze it, and we don't want some other factor associated with having children that would impact whether or not what the outcome of this would be, other than whether to have children or not. Okay, so in other words, we wouldn't want to sample only women who had children in an older age and compared them with women who didn't have children who were young, for instance. So we wouldn't want any kind of confounding factor like that. So it is an independent sample. Okay, so, okay, next one. And by the way, you can interject here, ask me some questions and stuff like that if you want, or if you have a particular issue on this particular homework you want me to skip down to, let me know. I'm going to go through them pretty quickly. Air quality measurements were collected in a random sample of 25 countries. Again, a random sample, 25 countries in 2013, and then again in the same cities in 2014. Okay, it's kind of a key, right? We're sampling from 25 countries, initially randomly selected. Okay, and then we're going back to the same 25 countries in another year and doing the same measurement. So right off the bat, you have to be thinking, well, gee, these numbers are going to be paired. These numbers, all these statistics are going to be paired. Should we use a one-sided or two-sided test? Type 1 for, okay, and those are the answers down here. Should we use a paired or a non-paired independent test? Okay, so first of all, number one, is this a one-sided test or a two-sided test? Okay, well, for starters, we don't know whether the air quality measurements went up or down. There's no indication in the question or any direction that we're going in terms of the analysis that indicates to us whether we believe that the average measurements in 2013 are higher or lower than they are in 2014. Kind of in the back of your head, you might say to yourself, well, this is always improving and stuff like that, air quality. It's getting more attention, but hey, we're in a phase now where, the EPA is getting some new restrictions and so on and so forth. We're rolling back some regulations and so on. So maybe you shouldn't make that assumption for this kind of thing. Certainly in this question, they didn't make that assumption. So this is a two-sided test. Okay, our null hypothesis is going to be that the mean air quality measurements for 2013 equal the mean for 2014, and our null hypothesis is the mean for 2013 does not equal the mean for 2014, two-sided. If we were to believe that the only thing that could be is lower in 2014, right? In other words, that the mean for 2014 is less than the mean for 2015. That would be a one-sided test. We could do a one-sided test, but we would have to have a really strong argument for saying it could only possibly go that direction. Okay, so in that case, the mean, the mu1 is less than mu2, whichever way you define it, right? 2014, mu for 2014 is less than mu for 2013. And your null hypothesis would be that the two means are equal, or yeah, okay. I'm not sure it's a new question. I'm still kind of discussing that, so there's a little bit of a lag here sometimes. Let me open up a Word document here so I can type in here. Okay, let me get a new blank document. I don't have my graphics tablet available to me right now. Let me make it a little bigger. Okay, so let's say the mean for 24. We're interested in the mean air quality measurement for 2014, and we're comparing it to the mean for 2015 or 2013. Let me give that a lowercase. Okay, so if we were talking about a one-sided test, right, or a two, let me start with a two-sided test. A two-sided test, we would be saying that we don't know which of these two is going to be larger or smaller. We're only interested in proving that 2013 is not equal to, hang on a second here, let me, not equal to the mean for 2014, right? That would be a two-sided test. Okay, in other words, we would reject the null hypothesis if either of those cases is true. 2013 is less than 2014, or 2013 is more than 2013. That would be a two-sided test, or a two-tailed test. Two-tailed test is okay too. So now, normally, we would go to answer that, William, to answer your previous question. Normally, this would be our default null hypothesis and alternative hypothesis. In other words, our null hypothesis would normally be that the two of them are equal. That's where we would start, right? So that's normally where our null hypothesis would start when we're doing a two-sided test, or when we're doing a one-sided test. The equality is always in the null hypothesis. Okay, the equality that we're talking about is always in our null hypothesis. Let me put in H-alt. Okay, let me tap these over a little bit. Okay, so now let's take a look at what happens when we have a one-sided test. In a one-sided test, okay, and I'm going to do this backwards. I'm going to start with my null hypothesis. In a one-sided test, I'm going to say to myself, you know, I'm sure that the mean level of air pollution in 2013 can only be greater than the mean in 2014. That's the only way it could happen. So my null hypothesis stays the same. My null hypothesis is that there's no difference. But what I'm saying, when I have a one-sided alternative hypothesis, what I'm saying is I know it can't be lower. It's impossible for it to be lower. We instituted all these laws. We burned less coal. It could only be lower. So I'm going to prove whether it's the same or lower. Now, many times what you'll see in here is, besides the equal sign, they'll also put in null hypothesis that it could be equal to or less than. Right, so you'll see that also, but the really important part is there that has an equal sign in there. Okay, so that's our one-sided test. Our two-sided test is a more rigorous test. Why is it a more rigorous test? Because if I'm only willing to have a 5% chance of being wrong, and we remember that that's 5% in the tails of our normal distribution for our samples that we could, all the possible samples that we could have. Okay, if I'm only willing to have a 5% chance of being wrong, well then I can only tolerate 2.5 in a two-sided test. I can only tolerate a 2.5% chance of being wrong on the low side and a 2.5% chance of being wrong on the high side. In other words, the reverse of 2013 and 2014 being larger and smaller. On a one-sided test, since I'm only going to test whether one is greater than the other, not both ways, right? Then I can afford to put all 5% of my probability of being wrong on one side of that normal distribution. Okay, and that means that I don't have to have my two means to as far apart as I do with a two-sided test. Two-sided test, my means have to be further apart, so I'm further away from each other on that normal distribution of all the possible samples. So two-sided test is more rigorous, and we normally almost always do a two-sided test unless we can really justify doing a one-sided test. So this is a two-sided test. The issue of paired or non-paired is a completely separate issue. It's a paired test. It's a paired test because we're actually measuring the same country twice, before and after. So we can afford instead to just test the differences between each country before and after. It almost becomes like a single sample t-test, right? Because we're only looking at the differences, not the mean of one versus the mean of the other, just whether or not the average of the differences is different than zero. Okay, so it's going to be a paired test. Hope that makes sense. Hope I explained that okay. Okay, did that help, by the way? In each, I'm going to move on because while you're typing. Oh, good. Okay, I hope so. In each of the following scenarios, determine if the data are paired. Type P for paired data and not NP for unpaired data. Okay, so let's take a look at these. Gender-related salary gap by comparing the salaries of randomly selected men and women. Well, it's random selection. It's men in one group, women in the other group. So obviously, it's not the same people sampled before and after something. So that's not going to work. Compare artery thickness at the beginning of a study and after 2 years of taking vitamin A for the same group of patients. One group of patients we're testing them before at the beginning, giving them vitamin E, testing the same people again afterwards, and looking at the differences for each individual. So that is indeed a paired sample. Assess the effectiveness of the diet regimen by comparing before and after weights of subjects. Again, right? That's same subjects before and after. Assess health inequality by comparing infant mortality rate, risk of between birth and 1 year, between Iceland and Mozambique using data collected by World Health Organization. Well, you're actually comparing the health in two different countries, right? But you're not comparing it in 1990 versus 2000 or anything like that. You're actually comparing the numbers which have been collected for those two locations. Okay, so that's not going to be paired. Okay, not paired. Okay, again, that kind of like if you read the language there and you figure out that you're really measuring a difference in the same individual, in the same country, in the same group, then it's pretty easy to figure it out. Yeah, it's kind of like apples to oranges. In fact, it really doesn't. It really doesn't even give you a real insight into what they're doing here, because assess the inequality, infant mortality rate in one country versus the infant mortality rate in another country. It doesn't tell you whether they're looking at it uh, 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 over a number of years, comparing. In other words, it doesn't tell you what the data is besides a single number. In other words, this could even be just a single number that's reported by the World Health Organization. You're comparing the two numbers, so I'm not sure exactly what they would mean by that. It's definitely not a paired sample. Okay, so if they ask us for anything else, we'd really have to have more information. Okay, interpret the given confidence interval. A researcher wishes to determine whether people with high blood pressure can reduce their blood pressure by following a particular diet. Subjects randomly assigned to a treatment group or control group. The mean blood pressure was determined for each group, and a 95% confidence interval for the difference in the means for the group versus the control group. Mu1 minus mu2 was found to be minus 21 and minus 6. So this is a confidence interval for the difference. If there's no difference in the performance of the diet, you would say to yourself, well, we would expect the difference to be 0. So the fact that this is -6 to -21 suggests that the dieting group lost weight, right? Because we don't have 0 between these two. You would reject the null hypothesis that there's no difference in the amount of weight lost on the control group and the or blood pressure on the two groups. Okay, so it looks like there is a difference. We reject the null hypothesis. Okay, so let's look at the various statements. Okay, we're 95% confident that the average blood pressure of those who follow the diet is between 6 and 21 points lower than the average who do not follow the diet. Okay, now I could even just have left this out, the 6 and 21 points out. We're 95% sure that the average blood pressure was lower in the group that followed the diet. Why do I say that? Because we're 95% sure that the difference was less than there was a difference, right? It was less that a 0 is not included in the difference. Okay, so you could say between 6 and 21 points lower, because we're not sure how much lower, but we're 95% sure that it was between those two numbers lower, which means that it's different than no difference. The probability, let's take a look at why these others are not true. Probability that the mean blood pressure for those on a diet is lower than for those not on the diet. The probability that the mean blood pressure for those on the diet is lower than for those not on the diet is 0.95. Well, you could kind of deduce that. In fact, it's probably more than that, right? It's probably more than 95% for starters, because it's quite a bit different than 0, right? But the confidence interval really tells us, it gives us a little bit more information than that. Okay, the probability that the mean blood pressure for those on diet is higher. Did I misread that? The mean blood pressure for those on diet is lower than, okay, probability that the mean blood pressure for those on the diet is lower than for those not on the diet. Well, it's at least 95, but I would, and also we don't like to use the confidence interval quite that way. The probability that the mean blood pressure for those on is high, we know that's not true. It's the other direction. We're 95% confident anyway, even though it's the same statement as above. We're 95% confident that the average blood pressure of those who follow the diet is between, no, again, the wrong direction. Since all of the values in the confidence interval less than 0, we're unable to conclude that there's a difference. Well, that's completely wrong, because since they're different than 0, we can make that conclusion. Okay, assume the conditions for inference with a two-sample t-test are met. Test the indicated claim about the means of two populations. Compare the effectiveness of water softener using filtering to one not used to not filtering. They randomly selected 90 locations, divided them into two groups of equal size. Group A for water softener with a filter. Group B used only a water softener. At the end of 3 months, water samples were taken. Water softeners were measured on a scale of 1 to 5. The results were as follows. Okay, so what we have here. So for Group A filter, the mean was 2.1. For Group B, the mean was 1.7. So our null hypothesis is that the mean for Group 1 is equal to the mean for Group 2. Okay, we've got a difference. Now we have to figure out whether that difference is great enough. That's largely going to depend on the variability. So if I look at the variability standard deviation for Group 1, it's 0.7. If I look at the standard deviation for Group 2, it's 0.4. There's quite a bit of difference in the variability. So in this case, we're comparing two means, right? Our null hypothesis is that the means are equal. Mean for Group A is equal to mean softness for Group A is equal to mean softness for Group B. And our alternative hypothesis is that they're different. Let's go back to take a quick look at here, see if there's any indication that we could only have a lower water softness with or without the filter. And they really don't tell us that, do they? They're evaluating the performance of the filter. So we don't know for sure whether it's going to be greater than or less than with or without the filter. So it's a two-sided test. So the equal sign and the not equal is in the null hypothesis, and not equal sign is in the alternative hypothesis. Two different means. We see there's a difference. The standard deviations are quite different, right? So we can't assume equal standard deviation. One is more than double the other, right? Am I right about that? Is it more than double the other? Well, it's quite a bit more than the other, right? Not quite double, quite a bit. And so we would use whatever rules that we would want to calculate this manually. Most of the time, we're going to use SPSS. Our SPSS output is going to give us a test statistic, okay? And it's going to calculate for us a t-test value, came out to be 3.3. Going to calculate degrees of freedom for us, okay? And we can see how that was, remember how there was a version of this calculation where the degrees of freedom were rather elaborate calculation. I think probably when they probably pooled the standard deviations in this case. Okay, but whichever way, SPSS, we did it SPSS, and our p-value is 0.0014. So between the degrees of freedom and the variability, our t-test came out to be 3.328. And our p-value became a p-value probability that we would get this large a t-value if there were no difference between these two means given these samples, okay, is less than 5%. So our chances of rejecting the null hypothesis and being wrong is less than 5%. So let's take a look at what our options are here. Okay, p-value is less than 0.05. We're unable to reject. That's wrong, right? But when it's less than 0.05, we usually can reject the null hypothesis. P-value less than, we reject an alternative hypothesis and conclude that there's well, again, we don't reject the alternative hypothesis ever. We fail to accept it, right? Or we fail to reject a null hypothesis. We only accept the alternative hypothesis when we can reject the null hypothesis. So we know it's not that. Cannot draw a conclusion from the above information? Well, actually, we can because our p-value is so low. Since the p-value is less than 0.05, we accept the null hypothesis, wrong direction, right? We reject the null hypothesis. And then finally, since the p-value is less than 0.05, we reject the null hypothesis and conclude that there is a significant difference. In other words, we accept the alternative. Reject the null, accept the alternative. If we don't, if this were greater than 0.05, we just simply say we fail to reject the null hypothesis. That doesn't mean you accept the alternative hypothesis, right? You just fail to reject the null. Okay, now let's see. Assume. Okay. Okay, researcher wishes to determine whether people with high blood pressure can reduce their blood pressure by following a particular. Did I just backtrack? Right? Nope, I didn't. Okay, test. Okay. Reduce their blood pressure, a particular diet, similar to the question we had before, similar layout to the question we had before. Test the claim using a significant level of 0.05. Okay, let's take a look at this. We have two groups, right? We have two means we're comparing. Mean from group 1, mean from group 2. We have the variability of the two groups. In this case, the variability is pretty close. They're definitely going to be pooling the standard deviations. Okay, our sample size, 85 of one group, 95 for another group. Okay, so using SPSS, we would get a result, and it would be for likely, almost certainly, in the situation where the variability is the same, the row that has the variability being the same, no difference in the standard deviations, basically. And our test statistic comes out to be negative 2.3565. The only reason it came out to be negative is the order that we use these two means. In other words, we call group 1, we call this the treatment group, group 1, and control group, group 2. If we had reversed that, that would have been the same number, just positive. So it really doesn't mean anything. Okay, so now, but the only problem is I see a little issue here, and that is use the sample data to test the claim that the mean mu1 is smaller than the control population, is lower than the control population mu2. right? So we're looking at a single-sided test. They're saying do a test to show that it's smaller than. In other words, we're only examining smaller than. So what does that mean when we're only examining smaller than? Well, that means we're doing a one-sided test. So remember, our null hypothesis always has an equality, right? So it's always going to be mu1 is equal to mu2. Our alternative hypothesis is where our inequality is going to be. Okay, so our inequality here is mu1 is less than mu2. Okay, mu1 is less than mu2. So in other words, we will reject a hypothesis if, if mu1 is less than mu2, and we're only testing that possibility. We're not entertaining the possibility it could be the other direction. So mu1 less than mu2. In fact, you can see mu1 is less than mu2. The mean for the sample mean is less than the control mean, in fact. Now, is it a big enough difference? Well, turns out that the t-test that we run with SPSS gives us a result of minus 2.365 with a p-value of 0.096. Okay, now things can get a little bit hairy here because we don't have a lot of information. SPSS often gives you a two-tailed significance, two-tailed test, right? So we're not sure if it's one tail or a two-tail, but it's less than 0.01. So it's really not going to matter whether it's one-sided or two-sided. Yeah, this is a one-sided test. Okay, so reject the null hypothesis, conclude that the mean blood pressure level is lower for those who follow the diet than for the control group. Normally, our alternative hypothesis is that it's different for the blood pressure. It's different for those who follow the diet than for the control group, and then we make our conclusions separately from that. Okay, I'm not going to go through the rest of these because that's basically the real issue here is that it's a one-sided, they defined it as a one-sided test instead of a two-sided test. This is less rigorous. It's easier to prove. Our t-value and our p-value are large. Our p-value is a larger number because our t-value stays the same, but our p-value is a larger number. If this is a if this were a two-sided test, I presume they corrected it. If it were a two-sided test, if this is really the result for a one-sided test, then a two-sided test would have been 0.0048 instead of 0.96, right? It would have split up the p-value between the two sides. I can't tell from here whether they really did or not. I mean, we could do this by hand or try and simulate this in SPSS and figure that out. But it is a one-side. They are asking one-sided test. Now, just so you know, very frequently, if they put the less than sign here, a lot of times you'll see this with a greater than sign here. Okay, Professor Weicha uses this format mostly, right? But just so you don't get confused, a lot of times you'll see this here as well, because if you're saying the alternative hypothesis is that mu1 is less than or greater than, then a full description of your null hypothesis would be mu1 is equal to or greater than mu2. So you'd cover all the possibilities, or you can just leave it like that. Okay, just so if you see it that way, you will recognize it as well. Okay, so if a hypothesis test has a significance, mu1 if ever mu2 does not, then the corresponding confidence interval does not contain zero, and that's true. We know that, right? In other words, in SPSS, you'll often see that table. At the end of the t-table, it also has a confidence interval for the difference between the means, and typically, if the p-value, the t-test and the p-value tell you can reject the null hypothesis, then that confidence interval is going to say that's not going to include zero. No difference between the two means. In other words, if you can't say with 95% certainty that there's no difference between the two means, that the difference between the two means, mu1 minus mu2, is not zero, then you really can't prove that, in fact, that the two of them are not equal. Okay, so that's true. Hope that makes sense to you. Background characteristics. Some of these questions, rather than making you actually do an exercise, kind of test your understanding a little bit. Background characters of participants involved in the study between two equal groups, low carb versus conventional. Does the data suggest there are significant differences at 0.05, alpha equals 0.05, in participant characteristics between the different diet programs? Okay, so this is what we have here. We have the mean age is in these two programs is 52.1. The mean age in the conventional is 53.4, and the p-value for the difference between these two means, right, is 0.752. In other words, the t-test was done, p-value is 0.752 for the difference between the two means. Mu age for low carbohydrate diets equals mu age for conventional diets, right? And the p-value for the difference between the two is 0.752. Do we reject the null hypothesis? No, we don't, because there's more than 5% chance of being wrong if we reject the null hypothesis. How about the proportion of men versus women in these? It was 42 men in here. There were 34 men in this group. Is there a difference in the proportion of men in the two groups? Is the proportion of men in this group equal to the proportion of men in this group? And it turns out that the p-value is 0.015. So that one we can say with better than 5%, better than 95% certainty, less than 5% chance of being wrong, that P1, the proportion of men in group 1, does not equal the proportion of men in group 2. How about mean educational level? Again, less than 0.05, so we can reject that null hypothesis and say they're different. How about income? Well, no, we can't say that the income is different because the p-value is greater than 0.05. Okay, do we get that? Did we get that right? Right, that's a no, a yes, and a no. Yeah, we got it right. Okay, good. That's always comforting. All right, let's take a look at the NC birth my data set, our nemesis that keeps coming up. Okay, mothers are using these test the following hypotheses at alpha is equal to 0.05. Okay, so average mother's age significantly difference between mothers who smoked during pregnancies and mothers who didn't smoke. Okay, let's actually open that up and do that in SPSS. See if I get the same answer that they have here. Okay. Let's see, open. Must have opened it recently, right? Yeah. Let's see if I can't find it right away without having to search. Okay. I'll leave the output page up. So we were comparing, if I recall correctly, we were comparing the mother's age, which is the variable M age, mother's age, to the smoking variable, whether or not person smoked or not. Okay. Da-da-da. So mother's age, okay, so let me find that. Let me go back to SPSS. Okay, so let's give this a try. Okay, so we're going to look at mothers who smoked versus mothers who didn't smoke. In terms of the average age, the mother's age is a numerical variable. The smoking status is a categorical variable. Yes, they smoked during pregnancy. No, they didn't smoke during pregnancy. So we have a numerical variable that's divided up into two groups: mothers who smoked or didn't smoke, categorical and numerical. So I'm going to look for a difference in the average age of mothers who smoked versus the average age of mothers who didn't smoke. Okay, so let's analyze. Let's see, we're going to compare means. Independent samples t. It's not a one sample t-test, right? Not same women, not comparing it to a fixed value. Independent samples t-test. Okay, and my test variable is going to be my age of the mother, M age, right? And my grouping variable is going to be whether or not the mother smoked during pregnancy. Now, SPSS is going to ask me to define what number represents smoking and non-smoking. I just should have checked it before. I didn't. So I'm going to put in 1 and 0, see if we get lucky. I'm going to click OK. Okay, let's see if we got lucky. Yeah, it looks like we got lucky. Okay, so let's take a look at this. Okay, so the mean age of mothers who smoked was did not smoke is 27. Mean age of mothers who did smoke was 25. Looks like mothers who were younger were more likely to smoke. Okay, so standard deviation was very similar. Okay, equal variances are going to be assumed. So, and I'm going to go down here to the t-test and take a look at what that looks like. T-test is 2.92, and our p-value for a two-sided test, in other words, we didn't make an assumption before or after that who was going to be lower, who's going to have lower or higher age, is going to be 0.02. So we can reject our null hypothesis. And while we're here, whoops, can't grab that. Well, let me grab that. Let me try again here. Okay. I got it that time. The 95% confidence interval for the difference between these two ages, right? 25 minus 27 is about 2 years, is about a year and a half. 25.7 is about a year and 1.5. The 95% confidence interval for that year and a half difference is really 0.2 years to 0.7 years. So those are most positive numbers. So we're 95% sure that the difference in ages for women who, average age for women who'd smoked versus average age for women who didn't smoke does not include 0. Does not include the possibility that there's no difference because it's outside of our 95% confidence interval for the difference between the means. So this, like that earlier example, this confirms what we saw when we did that, when we looked at that earlier test. Okay, let me go back here and take a look at it on our problem. Okay, and let's see. Okay, oh, I got to the wrong one there. Okay, let me go back to this one. Okay, so our mean values were, let's see, 2.33. Looks similar to what we got, right? P-value is 0.01. We can reject the null hypothesis since it's less than 0.05. 0.21 is less than 0.05. Okay, so we get the same outcome as they get. And our null hypothesis, two-sided test, it's this phrased a little bit differently here. We could say mu1 is equal to mu2, and mu1 is not equal to mu2. Another way of phrasing null and alternative hypothesis that fits that 95% confidence interval technique at the end, for which we get the same result, okay, is mu1 minus mu2 is equal to 0. You can imagine, just move this to the other side, and you have the way we usually phrase it, and mu1 minus mu2, if you move that to the other side, you have the same thing also. Okay, so let me put this away. And here's a number of the output tables as well. Okay, now, okay, now the next question involves evaluating. Let's see if I can even find the question. Next question involves evaluating whether or not a mother is more likely to. I want to go over this because now we're looking at a new test now. So we judge when we use what test we use is based on what kind of data that we're comparing. So let me go back here. The percentage of who smoked is different than the percentage of premature infants born to mothers who did not smoke. Now, okay, so we just dealt with the average age in the previous problem. I don't know why she used this one. I would have used this one up here. The variabilities are the same. In the previous one, we dealt with we compared the two average ages for the two groups. In this one, we want to know whether a mother that smoked is more likely to have a premature infant or not. Let's think about that. Mother smoking, variable number one. Mother smoking is a yes or a no. Either she smokes or she doesn't smoke, right? That's a categorical, numerical, nominal categorical variable, whichever way you want to call it. What about whether or not she has a premature infant? Well, in this database, there's a variable called premi in which we have a value for babies that are premature and another value for babies that are not premature. Two choices. Again, a categorical variable. So we're looking for an association between one categorical variable and another categorical variable. 0 and 1 and 0 and 1. We're looking for an association between those two. And we know when we're working with two categorical variables, what we're dealing with are a proportion, percentage of women who smoked that have premature babies. Or another way we could look at it is a contingency table. The exposure is smoking, and the outcome is did mothers who smoked, how many premature babies did they have, how many were not, and so on and so forth. So we can use our chi-square analysis, or we can use our odds ratio and relative risk to determine whether or not there's an association between these two variables. But again, this time around, we're dealing with categorical variables both ways. In fact, let's go back to SPSS. Let's do that right now. Okay, and by the way, the way they determined what was a categorical variable, what was premature and what wasn't premature, is they simply just took the weight of the infant or the number of weeks of the pregnancy. I think that's in here somewhere, right? And they decided, well, if it's less than a certain number of weeks, you could probably figure this out if you went through the data very carefully. Notice the 0 and 1 also. If you went through the data very carefully. But they took the number of weeks of the pregnancy. Let's see if we can't see, for instance, this one is a 1. That pregnancy was only 36 weeks. So my guess is if it was under 37 weeks, let's say, well, 39 was a 0, so it's not premature. So my guess is around 36, 37 weeks, they decided to define anything less than that as premature. Okay, so that's how they got the zeros and ones in here for premature. So let's analyze this. Analyze. So this time we're not going to compare means, are we? This time we're going to go into descriptive statistics. We're going to go to crosstabs. We're going to set up a contingency table. In our rows is going to be our exposure, which is whether or not the mother smoked during pregnancy. And in our columns is going to be the outcome, whether the infant, well, there it is. It's in the description, less than 36 weeks. Actually, it's equal to or less than 36 weeks, it looks like from what we saw in the data. Okay, so I'm going to put that in there. Okay, and I'm going to go ahead and I'm going to go in here to statistics. And I'm going to ask it to calculate the chi-square value and to calculate the risk. And I'll click continue and OK. And here's our output table. So here is our contingency table. This is mothers who did not smoke, 606 babies that were not premature, and 78 that were. And with mothers who did smoke, it was 99 and 15. So it looks like maybe let me go back here for a moment just so I can get a little bit better look at this. Cross tabs. Okay, I'm going to also go into the cells and give me my percentages by rows. And I'll click OK again. Get a little bit more information. So 86.6% of the babies from mothers who didn't smoke were not premature, and 86.8% of the babies mothers who did smoke were not premature. So there's little or no difference between the two of these, isn't there? Right? In fact, if we look at the percentage of premature births, actually there's a little bit of difference, isn't there? If we look at this, if I look at it that way, 11.4% among were premature among mothers who didn't smoke, and 13.2% among mothers who did smoke. So I thought that was 88, so that's 86. Yes, that's 13, a little easier to see there, right? So one of the reasons why the table came out this way is because in this data set, we defined infant not premature as 0 and infant premature as 1, right? Problem there is that SPSS always sorts this by alphabetically or by number. So if we had made this 0 and this 1, right, then these tables would have been reversed and the 11 and the 13 would have been here. It would have been a little bit easier to interpret this. But let's do our chi-square analysis to see if there's an association between pregnancy and smoking. We can see there's a bit of a difference. Like for instance, I can see, for instance, that 13% versus 11%, it looks like the risk of having a premature baby is roughly about 15 or 20% greater than if the mother smoked than if she didn't smoke, right? So, although 13.2 over 11.4. Right, so let's take a look at this. So is this big enough difference for us to say that there's that we can reject the null hypothesis that there's no association? So from the results here, our chi-square value is pretty small, and our p-value, our two-sided test, is 0.589. Doesn't look like we can reject our null hypothesis. How about our risk? Well, here's our odds ratio for smoking during pregnancy is 1.777. Okay, but we'll look at our 95% confidence interval. We'll include 0, so we can't say that our odds of having a premature birth due to smoking is different for mothers who smoked versus mothers who didn't smoke. Is different than 0. Okay, it's different than 1 in the case of odds ratio. Okay, let's go back to what they got in the problem, see if they were using the same data that we were. Up, and there we go. And sure enough, we can see that that's the same result that we got. Okay, and in this case, they actually did a manual test, calculated confidence interval for the two proportions, right? This is our pooled proportion, right? A pooled standard error, right? And they found that that the difference between these two is 0.02, and our confidence interval wound up including 0. So we couldn't reject the null hypothesis from there either. A lot of ways to skin a cat here. The easiest way to skin a cat, obviously, is to use SPSS. Okay, so well, I think that was the last problem there. I just want to maybe get. I'm not going to say that. It's just the answer sheet. Okay, so I'm going to skip quickly over to the current version. Rather than I'll go over 11 on Wednesday. You know, we have a short. I'm going to be on the road on Wednesday, so I can't promise to do it quite as long. But and I'm not sure what my internet access is going to be like, so I'm a little bit leery of promising too much for Wednesday. But I'm certainly going to give it a try. Let's go into what our current homework. I'm not going to show the answers here. I'm just going to show the questions. And I'm just going to quickly go through here and say, okay, let's see. Well, here, clearly what we're looking for here is correlation of negative 0.9 indicates a stronger correlation than correlation of 0.5. And we know that being closer to -1 or +1 gives us a stronger correlation. So you can draw your own conclusions there. Correlation of association between any two variables. Anybody tell me question B is kind of a trick question. What's a trick question on part B there? What's the trick there? It's a measure of association between any two variables. Well, there's a measure of association between two variables, right? What kind of variables? Those of you that I haven't put to sleep yet, type something in. Continuous, right? Numerical variables, right? Only association between two numerical variables. Okay, again, you can see that there's an association here. For instance, that's a linear association. And you can figure out, you remember that if it slopes up, it's positive. If it slopes down, it's negative. Okay, and you can make your own conclusions about this again. Okay, it's positive or negative. And this one over here, whether you think there's an association at all, and so on. Okay, so these, I think you'll have no problem with these. Would you expect, given the length between a human's femur and a human's humerus, you would expect a positive correlation, a negative correlation, or no correlation? So what do you think there? Let's get an opinion there, right? Got big arm, you figure you got big legs. Got big thigh bone, big, right? Yeah, positive. Positive correlation. I would certainly expect a correlation, right? Don't see too many people with Although, there are some people, I remember that. You ever notice that when a big boxing match comes up, that one of the two things, okay, I'll do that. I got a note. Okay. One of the two things that comes up with when they have a boxing match is they a lot of times in newspapers they'll put a title on it, the tail of the tape, the measuring tape, and they'll have the boxers side by side, their height, their weight, and so on and so forth, and they'll have their reach, and the reach will be a number if they put their arms out, stretched out like they're on a cross or something like that, stretched out. They give their arm length from fingertip to fingertip stretched out. Now, believe it or not, you guys have all seen that circle with the Da Vinci circle, the famous Da Vinci man inside the circle with his arms and legs stretched out. Believe it or not, for most people, the length from fingertip to fingertip is pretty much the same as your height, right? But you'll notice some very good boxers, their arm length is disproportionate to their height. And I remember Muhammad Ali had an extra was his reach, the length from fingertip to fingertip was quite a bit more than his height. So that helped him with his jab and his keeping distance and so on and so forth. Made him a much more effective fighter. So it's interesting, that sometimes you get some anomalies there, right? So okay, so I'm going to jump to questions 13 through 15 because I think they might be causing some issues. Okay, let's look at the problem for starters. Okay, Child Health Organization is investigated a range of topics in order to model infant weights, following variables of interest, multivariate linear analysis, length of pregnancy, but a whole bunch of stuff. Okay, so let's see what we got. Okay. What percentage of infant weight is accounted for by this model? Okay, so what they've done here is they've done a multiple linear regression. In other words, they've tried to associate the what is the model? Infant weights. Is that a variable? Let me see if I can't. Let me just read through the problem before I get too involved, before I skip down too far. In order to model infant weights, the following variables of interest: the multi in days, 0 to 6 otherwise, mother's age in years, mother's height, pregnancy weight in pounds, mother's weight in smoking status. Okay, here we go. I got a little confused there because I saw weight as one of the variables that they were examining. That's the weight gain of the mother, I believe. Okay, so gestation is number of weeks. They looked at a variety of factors that they used as independent variables, right? Moved over into that box for predicting what the weight of an infant would be at birth. Okay, how many weeks of gestation, uh, 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 how many, whether or not it's firstborn child or second, not the firstborn child, the age of the mother, the height of the infant, I guess. I'm not sure what height they measured there. Height of the infant, I guess. Okay, and whether or not the mother smoked during pregnancy. So we're trying to predict what the effect would be on the weight of the infant. So these estimates are the slopes for the various values that are going to be in our formula. Y is equal to 0.44 times the weeks of gestation plus negative 3.33 times either 0 or 1 age. This would be negative 0.01 times the age of the mother height and weight. I guess I'm not sure where they got those from, but I'm gonna skip through that. But I don't think it's relevant anyway to the questions that they ask. What's the percentage of variability in infant weight accounted for by this model? Okay, you guys remember that the correlation coefficient was R. And we would then calculate from that R squared, right? And R squared is equal to 0.2468, right? You guys remember what we used R squared for? R squared gave us predicted for us what percentage of the variability in the independent variable Ry was predicted by the variable that we were examining, the x that we were examining. In this case, the many x's that we're examining. So I won't, you can draw your own conclusion about the actual number. Okay, it's in there, the percentage, right? But not a very high percentage, right? Given all those variables that we included. Okay, refer to the problem again. Well, which variable is not significantly associated with infant weight in the adjusted model? Okay, well, which of these numbers that go in front of ours, that which represent our slopes, right? Except for the intercept here, right? That's the y-intercept for the line. Which of these numbers is not statistically significant? Let's go over to our t-value and our p-value. Is there any that are greater than 0.05? Oh, look, I see one that's greater than 0.05. So maybe that one is not statistically significant. And maybe we have to make a judgment later on about whether included or not. Should age be included in the model? This is a complicated question here. It's more complicated than meets the eye. I'm going to leave it up to you to answer that, but it may not be the answer that you typically might expect. Okay? I'll leave it at that. Okay, there may be, even though it's statistically not significant, you may want to leave it in there for other reasons. But I'll leave that up to you to mull over a little bit, and then when the answers are available, I'll go over it with you. Okay, what's the average difference between birth weight what is the average difference in birth weight between infants born to mothers who smoke versus infant born to mothers who didn't smoke? Okay, well, I'm not going to take mothers who smoke versus didn't smoke. But instead I'll choose one of the other variables. Okay, so what's the average difference in mothers? I want a categorical. Parity, I think, is whether it's first whether the mother had babies before firstborn or babies before. So if I had to predict what would be the difference in weight for parity 0, parity 1, I would say it would be negative 3.33 ounces. Okay, so you can figure your own. You can come to your own conclusions on how you should calculate that there. Okay, for this particular problem. Okay, for a problem, which infants have lower average birth weight, firstborn or not firstborn? Oh, that's parity. Oh my goodness. Okay. Okay, so 0 if it's 0 is firstborn and 1 is otherwise. Okay, so how would we know that? Well, we know that the way parity influences the weight of the infant. Okay, and this one I'll work with you on. Okay, parity influences the weight by reducing. In other words, if 0 would be lower than 1. So in other words, in front of the x that represents the parity. Remember, this is all based on a formula we created. Y is equal to x for gestation times 0.44 times x for gestation plus minus 3.33 times x for parity, the value at parity, times plus rather negative 0.01 times the age times 1.15 times height, and so on and so forth. So parity is negative 0.33. So if I go back here, if 0 is the firstborn child and 1 is other, okay, which has a lower average birth weight, firstborn or not firstborn? So who gets the lower average birth weight, 0 or 1? Okay, so let me go back here again. Okay, so this portion of my y value, y is equal to, I'm going to forget all the others, y is equal to negative 0.33 times parity. If I say that parity is equal to 0, negative 0.33 times 0 is 0, so parity does not contribute to the value of y. But if parity is equal to 1, then y is equal to negative 0.33 times 1, which is negative 0.33. So parity suggests that 1, if the value of 1, if you're not firstborn, your weight is going to be lower, right? It's going to be 3.33 ounces lower on average. Okay, firstborn, because what's the question? Which has a lower average birth weight? Well, I would say then it's going to be not firstborn, right? Because their parity be equal to 1. Okay, and what about the intercept? Yeah, the intercept is where it crosses the y-axis, and to be honest with you, that really doesn't make, you're really not going to use that very much, right? Because that really helps you to predict the weight in the end, because that's kind of that kind of like helps define your straight line. There's always going to be a y-intercept where it's going to cross the y-axis. In addition to all these slopes, the overall slope is only going to give you the slope of the line. It's not going to tell you how high or low the line is. So you need that y-intercept. But it really doesn't figure into the predictive value of all these other variables, gestation and so on and so forth. So you do need that. In fact, in a lot of cases, the intercept is a number that's impossible anyway. So in other words, when x is equal to 0, when all these values are equal to 0, right? When the average slope here is all equal to 0, right? Well, then the weight of the infant is minus 80 ounces, right? And we know we can't have an infant minus 80 ounces. So the y-intercept really doesn't even have a physical meaning here, but it's needed to describe that straight line. Got a question here. Is parity a part of every data table when you examine? No, they just asked for parity here. In other words, they could have, remember, in simple linear regression, they would have only examined one value, right? Only gestation. Or they might have only examined the age of the mother and forgot about everything else, or whether the mother smoked or not, in order to produce a formula which predicts what the weight of the infant is going to be. Okay, they might have only used one of those variables. In a multiple regression, you're trying to combine all of them together so you have better predictive value. So you raise that R-square number, right? So parity just happens to be one of the variables that they decided to include in this analysis. If it was you doing this analysis on your data as part of your project, and you decided to do multiple linear regression, you would decide, well, for instance, you would decide whether someone's blood pressure is equal to, and what variables you think might influence blood pressure, like age and BMI and so on, and combine those variables that you would choose to be predictors, be independent variables that might predict someone's blood pressure, height, weight, and so on. Okay, so you could choose those yourself. In this case, you were given all of these are the variables, right? And this is the happens to be the y-intercept, right? So it would look a little bit different on that table. Okay, so I'm going to call it a morning, and I'll post this today, and we'll do this again. Email me again. One of the reasons I went down to this last question is because someone sent me a note saying that they had some issues with the last few parts down here. So if I know that it's a specific issue with specific areas, then I can react to that and maybe make sure I cover that while I'm doing this. So it always helps for me to get some of that feedback from you guys. Again, put BIOS 610, BIOS 610 in the subject line. Send me an email, Or if you're online, you can just type in chat. Yeah, as a matter of fact, what I'm thinking of doing on Tuesday night for the lab, we're going to do logistic regression. I'm not sure how many guys might use that in your actual projects and stuff like that, but I'm hoping to spend a little bit of time on logistic regression, but start the process on Tuesday night, and then again maybe continue a little bit on Wednesday night, and then again next Sunday, and basically give you guys a bunch of different data sets or different selections of variables, and say, okay, this is what we're examining these variables. What test do we use? How do we run SPSS? Right. So you get to see each one of those things. I'm also going to give you a link to a variable. Somebody asked about grouping variables to create charts in SPSS. I'm going to give you a link to a YouTube video that's pretty good on that. Rather than spend time doing it here, maybe if it's not clear, I can go over it again. And also at some point, like once we get this past this exam, then we can really kind of zero in on the projects and stuff like that and spend some more time individually. Okay, so I hope that helped. And like I said, we'll pick up from here on Wednesday and then continue on Sunday. Okay, so have a good rest of the Sunday today. Hopefully, maybe the weather will hold out for us a little bit. Bye, guys.